gaps. So, there is an equation. Now, this equation here, gentlemen, we've been looking at the rate of heat transfer. So I would like you to, just next to this equation, we're going to take that little t, which is time in seconds, and we're going to divide both sides. So I would like the equation to be Q on T equals E sigma A T object to the fourth power minus T surrounds to the fourth power. T of the object. Have a look, it's written here, the temperature of the object. It has to be in Kelvin. Now, guys, I was a bit disappointed yesterday when no one was able to tell Mr. Khan how to convert to Kelvin. That's going to be in the test. You need to be able to convert.
Someone did.
Well, we finally got there. You add 273.
Yeah.
Okay. The issue is our temperature scale has to be an absolute. The issue here is, look at this equation here. If you had something that was at 0 degrees Celsius and you put in T equals 0, it would say, oh, there's no transfer of heat. But we know that's not true. Any object above absolute 0 is going to emit infrared radiation, even an ice cube that is at 0 degrees. It's just not as much as a warm-blooded mammal at 37 degrees. So then, you go, all right, convert it into Kelvin. 273 to the fourth power. That's not going to work if the ice cube is sitting in a freezer at the same temperature. All right, so that's why we have to include the surroundings. Now, Daniel asked a really good question about why is the top one not including the surrounding temperature? And you could try this yourself. Once the difference in the two temperatures gets greater than 20, because you're raising something to the fourth power, it's huge. And if you subtract something that's a lot colder, even though that's being raised to the fourth power, it won't affect that massive value. Okay? So what I want us to do is I want you to focus solely on the object minus the surroundings. So we're not going to worry. That top equation is for like a star sitting in a vacuum. You know, if the star is 5,000 Kelvin and we have its surface, it's going to be pumping out a lot of energy. Okay? Now,
What's the T after the T on the
Time.
Oh.
down here. So again, that should really have been offset. T is time in seconds. This is a little formatting error there. That little T should be off to the side so you can see the values. Now, guys, this is called a Leslie cube. It shows us that matte black objects are better at emitting than gloss silver. At the moment, its resistance is slowly dropping. It's now at 42,000 ohms. This is the globe inside. Basically, no, sorry, it's not the globe inside. It's the metal, the actual cube itself. And on the side, it says when its resistance is 40,000 ohms, it has a temperature of about 46 degrees. Once it gets to about 5,000 ohms, it's at 100 degrees. There's a whole table on the side of this little box. I've set the power to 7, nearly at the top. There's a 100-watt globe in here that's slowly heating up the inside of this cube. The inside of the cube is all pretty much the same. It's just sort of polished aluminium. Once that plateaus, or once that settles, I'd like you to tell me. Because once it settles, I know that it's got a constant temperature. And we'll figure out what it is. It might be 80 degrees, it might be 90 degrees, whatever it is, that's what it is. Okay? And we'll come back and we'll measure the amount of infrared radiation that each side of the cube is emitting. Now, I haven't told you, each cube, there's matte black on this side, and then there's a gloss silver. The back side is a shiny silver, it's almost like a mirror. And this side is matte white. So we've got 4 different surfaces, but they're all going to be at the same temperature. Now, I spoiled the fun here, because we know that matte black surfaces have a higher emissivity, and they're really good at absorbing all radiation. Mr. Khan said it is not possible for E to be 1. Some light does escape. All right? So it's a theoretical black body. That's why they say theoretically, if we had an object that had an emissivity of 1, you wouldn't see it. Well, that's a black hole. But then they discovered recently, in the past 30, 40 years, black holes do spit out gamma radiation. They used to think that nothing could escape a black hole, but they've discovered some Hawking radiation, named after Stephen Hawking. And same deal here. It's impossible to have a 0 because the surface is made of atoms. You can have the smoothest, most reflective surface possible, but some of that light is going to cause the atoms to jiggle slightly. So it can be very close to 0, can't be equal to 0. Okay? If you had something that had an emissivity of 0, you could put it in an oven and it would never get hot. 1,000-degree oven and it's sitting there nice and cold. Doesn't happen. Okay? So, I'd like you to visualize these rays of light coming down and this idea here, it's called a black body, it's a theoretical object that has a cavity. And if you can have light that strikes it and it gets trapped in that cavity and there's ding, 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 it just keeps getting reflected inside and then eventually it all gets absorbed. So all of the energy gets absorbed. In science, most things, if you can play science in normal direction, the physics should also work if you press rewind. So have a think. The light travels in, it makes the atoms jiggle faster. Let's play that in reverse. If we have atoms jiggling fast, they go out. So most of you can understand absorbing infrared radiation. It makes sense. This makes sense. The emitting radiation is the trickier one. It's a bit weird to think that a matte black object would emit more infrared than a gloss silver if they're at the same temperature. Okay? But that's what happens. If I had the time, and maybe tomorrow if I get my act together, we could remember the experiment where we heated those two up and we got that curve over here? We got that curve, right? I'll just quickly write. This one here was my matte black, and this one was the gloss silver. Okay? Well, here, and I can prove it to you, you don't have to believe me, I'll show you with an experiment. If we put some boiling water in those same cans and we just let them cool, couple of statements. What could you say if we left them for a long period of time? What could you say about both of the cans? Yep. Liam?
The black one would cool quicker than the silver one?
Yes, it would cool quicker. What else?
Would both stop at one point?
Yeah, they would both reach their environmental, the room temperature, the equilibrium. So they'd both get to the same temperature, but the matte black one would get there quicker. Yes?
Oh, I was just going to say that's like one of the exact questions on the back.
Good. Awesome. Well done. Good. Just before we go on, there is an equation. There's an equation for this curve, and Isaac Newton came up with it. Isaac Newton was a really smart dude. Did I talk about how smart he was? Alright, there's a Mr. Murray story time in that. But anyway, he wanted to explain how the world worked back in the 1700s, but the maths at the time was too basic. So he goes, you know what, I'll just invent calculus. And so he invented calculus, which is a whole branch of maths that the year 12s do in, maths specialist. They're really tricky maths. And so there's some calculus here, and it's called Newton's law of cooling. Newton's law of cooling is basically describing that temperature curve over time. I'm just trying to clean this wet mud. It explains this curve over time. And it's actually a really useful equation. Because if you take a sample of temperature over time, eventually, I'm just going to quickly zoom in. If we didn't get it at the start, oops, I dropped my lab quest and I wasn't able to measure the starting temperature and it took 2 minutes to reboot, and I get this cooling curve here. Let's go from here to there. All right. So lesson finished early, it's Wednesday, weird Wednesdays. I wasn't able to get to 15 hours of recording. I had to stop here. And we only got that blue bit of the curve. Newton's law of cooling says that you could put an equation to that, but not only would it tell you what the equilibrium temperature is, what it would end up sort of flattening out as, it would also tell you the temperature that it started at. So the example they have in forensic science is you come across a body. sitting there. Stick your thermometer in it. It's not at the room temperature yet. This body died recently. And you can measure the drop of temperature over time, and you can actually figure out when that body was at 37 degrees. So in forensic science, you can use this to, providing no one turned on the air conditioner or come in and stole his jumper, they can figure out the time going backwards that he was at 37. Because he wasn't at 47, was he? Unless he died in an oven. I'm being silly. You're at 37 degrees, bang, you die. Your body temperature would do that. And after a long period of time, your body temperature would become room temperature. You're a corpse. So I just wanted to talk a few things about that. Have we plateaued yet? No, still dropping. Okay. Well, that's a shame because I want to use that example. Guys, at the bottom of page 13, do you have some blank space? Yes, you do. Go to the bottom of page 13, please. I'm going to draw my little Leslie cube. Here's my little Leslie cube. Okay? And I'll put one side is matte black and one side is gloss silver. Now here's where we're going to pretend an emissivity of 0.9, emissivity of 0.2. Okay? Obviously there's a lot more going on. There's a cable going in and there's a cable coming out. There's a dial here. There's a switch. Okay? Okay, there's my little Leslie cube. We're only going to look at two sides of the cube. And if this thing doesn't level out, we're just going to stop and figure something out. So, conveniently, that Leslie cube is 10 centimetres by 10 centimetres. So our area is 10 centimetres by 10 centimetres. It has a surface area of that many square metres. Yeah, I converted to metres before your very eyes. Let's look at the matte black. And our little row is 5.67 by 10 to the negative 8. Let's go to the temperature of our surrounds. The thermometer's sitting there and it was 20 degrees yesterday and I'm hoping that it's 20 degrees today. It's just under 20. Let's just say 20 degrees. 20. Here's what you all forgot. Plus 273 equals 293 Kelvin. Now, okay.
What's the one after that? Oh, no.
That's the Greek character of sigma. It's a Greek character because they ran out of letters of the.
Did you say it was like rho?
No, rho's the other one. Rho looks like a P. This one's the P on its. I don't know, the other way. Let's go 16,000 ohms. I'm running out of time here. When it's 16,000 ohms, it's actually at 68 degrees. It would probably burn me if I started to touch this now because it's getting a little bit hot. Let's just say 68 degrees. We'll figure out what it gets to. 68 plus 273. Quick mental maths, 341. Am I right?
Yes.
I don't know. I'm looking at Daniel because I think Daniel's good at mental maths.
Yeah.
Okay. So, that side is at that point in time, it's releasing heat at a rate of, well, let's go, E sigma A, T object to the fourth power minus T surrounds to the fourth power, throw everything in, 0.9. 5.67 times 10, and then you raise it to the power of negative 8. That's a really small number. Here we go. Object 341 to the fourth power minus 293 to the fourth power equals. And you're going to give me a number. And it should be less than 100 watts. Because there's a 100 watt globe in there. So we can't be letting out more than 100. We're breaking the rules. If this thing's putting out more than 100 watts, hey?
No.
Oh, guys, get your calculators out now.
Wait, so is that machine telling you the E value or the
E.
No, I guess the E value.
Oh, divide times
Okay.
In fact, if
Is that telling you the Q value?
I guess the E value, the data sheet here might actually give us the emissivity.
So what's that? So machine actually doing?
They do shift.
It's got them as a comparison. The black is at 100, the polished is at 7. So the polished has an emissivity that's 7% of the matte black. Yes.
Didn't you forget these stuff, Sarah?
Thank you.
Oh my god.
Oh my lord. Hang on. I'm going to do some quick. Oh, cheeky ninja edit. Here we go. Oh, I can't get him. Oh, yay! Thank you, Daniel. That would. There you go. You can hardly tell what it is I'm trying to write here. Thank you very much, guys. Calculators out, please. Yes. What do you got?
Wait, so this asking A surface area.
A is the surface of that side only.
Oh, only that side.
Yep. So guys, we are looking at the amount of energy that the matte black surface is.
Yeah.
Yep. So guys, I'm hoping you know how to raise things to the power of. You've got that little button, -8. Then you're raising that to the power of 4. Put this in brackets.
So,
Yes.
3.13.
Is that it? 3.13.
That's all I got.
Cool. Awesome. Good. This is good. 3.13. Oh, I mean.
You said actually less than 100. Seems like a lot.
Well, now hear me out, because, hang on, that's a good question. Well, we're only looking at one side of a 6-sided cube, so all of the others are also putting out energy. They've all got different emissivities, but the thing's still heating up. So some of that energy is going into the specific heat of the metal. We've got a big lump of metal here, just happens to have a hole in the middle with a light bulb. Once that plateaus, I can say that all 6 sides are emitting 100 watts, because as you get 100 watts into the cube, we get 100 watts out. But that will only occur when it reaches that equilibrium temperature, which it's still going at the moment. It's at 12. We're now at about 78 degrees, so we've gotten a little bit hotter. Yes.
So you know how it takes different surfaces longer to reach the equilibrium?
No, so the thickness of the aluminium, it's about 6 mil thick, so it's quite a large block of aluminium. It's only the outside surface that's different. Okay.
So it won't take the surface longer to emit.
It'll radiate different rays.
It'll radiate different rays.
Each one way.
So guys, this is all, boys, listening please. You're spot on. It's conservation of energy. If the light bulb's putting out 100 joules every second, then all 6 sides, if you add them all up, it would have to be 100 joules. Okay? At the moment, there's energy that's going into increasing its temperature. Once the temperature remains constant, then all 6 sides. Now, can I get Liam to come and look at this number here? Now, Liam's going to look at the voltage of this little meter, and I'm just going to point this meter at the different surfaces. I'm going to point this at the gloss silver side first. What does it read? 0.5. 0.5 millivolts. Then I'm going to point this bad boy at the matte black side.
Matte is black.
5.3.
5.3. It's nearly 10 times larger. It's over 10 times larger. So it's emitting 10 times more energy. It's the same surface area. It's the same temperature. It's the same Boltzmann constant. So the emissivity value must be 10 times greater. And so I was a bit wrong. I thought it might have only been 5 times greater. Turns out it's actually 10 times greater. If I point this now to the matte silver,
We changed to 0.1.
we're back down to 0.8. So the shiny silver was 0.5. This is 0.9. And then on this side, there's a matte white, which is 4.5. And matte black, what did we get it up to? 5.3. Okay. So it seems the matte white had a large emissivity. So it's this surface texture and colour. Okay. Now, I just wanted to see if this would play nicely. Recently, with the help of carbon nanotubes, they have been able to make the world's darkest material, that with the highest ever emissivity value. Let's see if we can watch this video without any...
It consists of many millions of carbon nanotubes. Each one of these tubes is as small as 2 or 3 nanometers diameter. And to put that in context, a nanometer is 1/1,000,000th of a millimeter. This is printed or grown on aluminium foil. Now, if I show you the rear of this, you can see that that foil is quite crinkled and creased. The eye picks those creases up very easily. If I now turn to the front, then there shouldn't be enough light coming off there for the eye to discern any creases or contours. The surface coating absorbs 99.96% of all the light that hits it. Now that is the darkest material that has so far been measured. We've had this measured by the National Physical Laboratory here in the UK and by NIST in the US, and they say they've never measured anything as dark. If you use Vantablack in stray light reduction applications, you'll see.
All right, so 99.96% of all light on it. So an emissivity of 0.9996. All right, so only 0.00004% actually gets reflected off the surface. So it's really bizarre. It tricks people's brains because you cannot see any surface contours. You can't see any shapes. I can't seem to do anything today. Show me the god. There we go. Thank you very much. It doesn't look very good on the projector. But apparently when people look at this Vantablack is the surface, it looks like somebody's just sort of ripped a hole in space-time and that you're staring out of the universe. Because you can't see any surfaces. A black object like this, I can see its surfaces because I can see some light reflecting. Even my iPad case, I can make out the texture of the iPad case because some areas are reflecting and some are not. I can see that there's sort of an embossed insignia. You look at any black object, you will be able to make out its surface, its shape. But with Vantablack, you see nothing. Nothing is reflected off, and so you cannot make out any shape. Now, yes?
So like when objects reflect light, you can't see it. Emit light, you can't see it. When they reflect it, you can.
When they absorb everything, you can't see anything.
But then they have to emit it, right?
Well, okay, so here's the thing. If we got this hot, it would be emitting a lot more energy.
So you'd be able to see it?
No, it would be emitting infrared. We turn the lights off, you won't be able to see the side of that 0.9 emissivity until it got to about 1,000 degrees when it would start glowing red. Yes, Ben?
What happens if its emissivity is 100%?
It would look even darker.
If it
and
absorbs or emits that much energy.
Well, hold on. There are lots of applications for this because for telescopes, if you're pointing something at a distant star, you don't want any background light or any light pollution. And so if you had this covering your telescope, you would be able to see further galaxies. With sonar and radar, if it absorbs all of that, you would be able to get better sort of imaging, medical imaging, military applications. There's a lot of applications. People are going, great, this is a brand new substance with brand new properties. Let's see where we can put it to make things better. Yes?
If it was 100% black.
Well, same deal. It would trick your brain and you wouldn't be able to see any surfaces. Okay? Now, I'd like you to have a go at these questions. This is beyond the syllabus. They're tricky. But Ben, if you can convert these temperatures into Kelvin, then that's half the benefit to you because there's going to be questions in the test about converting into Kelvin. Yes?
Do you have to add the 0.15? What is it?
0.15 for the Kelvin.
No. So just 273 is fine. Don't worry about the 0.15. So, has anyone had an attempt at these questions?
Matt has.
Have you done them all?
Yeah. No.
Okay. Keep working. So guys, here's the deal. If you get the 6 questions done, let me know. I'll put the solutions up, and then you can make a start on the revision booklet, which will prepare you for the test. But for now, I want you guys working through. I'll circle a few helpful things. Well, And remember our Stefan Boltzmann constant.
So what does TO mean? The outside temperature?
Temperature of the object.
Well, to do it to like 2 decimal places.
Ah, yeah, 2 decimal is fine. Ah, that's a good question. Yes? All of them. Good. What a beast. What a. Hang on.
Joules to the second -1.
Hang on. Oh my gosh, this just give us a second, Robbins. Well done, but before I've got to quickly sketch what's going on here.
There's no area.
For question 6,
You need the area. The area is 4 meters.
okay, ooh, a Coke can. Have you guys done the area of solid objects? You've got like a
Yeah.
pi r squared,
Oh yeah.
2 pi r h. So we need the height of a Coke can and the radius of a Coke can. Let's say the radius is 0.4 centimeters.
So do you always put it over T?
Oh, hang on. 0.04 meters. 0.11 meters. Sorry, question? Do you all? Yes, always Q over T.
So that's 4 centimeters. That's the radius.
Then let's just go with that, yeah? So what about this? This would be 2 lots of 0.2 by 0.04 plus 2 lots of 0.2 by 0.05 plus 2 lots of 0.04 times.
Where's the 05?
Well, you got 0.5 twice. You got 0.2 twice.
I just did all the
All right. So you guys have done 2 pi RH. No, sorry, 2 pi r squared plus 2 pi RH. So I'm hoping you guys have done this in maths, yeah? Finding good. Well, perfect. If anything, if you can tell me the surface area of a Coke can in meters squared, beautiful. It's all good. I'm helping you with your maths. Oh, look at that. Let me put I'll put the solutions up for you.
Should I grab the revision book?
Yeah, just grab one there. I will pause that. But also, I'm about to put the solutions up and you can go and check your work. Okay?
So I got one question.
Yes.
When it doesn't say the emissivity, what do you just put?
Well, it's just a number between 0 and 1.
Just put a random number. Because question 2 doesn't say the emissivity. Oh, no, sorry, it does.
Does it?
Yeah, it does, sorry.
Good. All right, 0.7. So remember, Mr. Khan said that it ranges between 0.6 to 0.8 depending on your skin tone. Okay, so that's frozen. Don't worry about question 7. It's tricky.